Hi everyone, let's start chapter 9 input modeling, and this is the first part of the pre-recorded videos. Let's see first where are we now on the course map. So we are on chapter 9 this week. So this means that after this week we will complete all the knowledge that we need to learn in order to build a simulation model. I mean a discrete event simulation model. So after this chapter, we will have all the skills and knowledge in order to build a simulation model, and then we'll learn how we can verify and validate a build a simulation model, and also how we can uh, infer the results obtained by a simulation model. Okay, so let's focus on input modeling or input data modeling in chapter 9 as the last part of building a simulation model block. In chapters 2 and 3 of our course, we were focusing on just building a simulation model and then implementing the simulation model in Excel or Arena. And the input data, the input models, for example, inter-arrival time or service time, those were given. But in a real world situation, in an actual system, when you want to simulate a real system, then that's your job to fit a distribution to the variables. I mean, the variable of interval time, the variable of service time. Okay, so you need and you have to do this. So, and it's called input modeling, and we're going to learn in this chapter how we can model input data for a simulation model. So to do so, at first, we need to collect data from the real system, and then we need to analyze the data and identify a distribution. So after collecting data, we'll do analysis on the data to see which family of distributions could be fitted for our data, and then we will estimate uh, the parameters of the chosen distribution, and after having the parameters, we can evaluate how the distribution is fitted to our data, which is called goodness of fit. So in this process, we can use some tools, for example, expert fit, stat fit, and so on, and Arena. Yes, Arena has a function, has a module that can be used for fitting distribution on any data set, and you will learn this week in the lab session how to do this in Arena. Okay. The data collection and fitting distribution, or let's say input modeling, is one of the most important and most challenging parts, jobs of a simulation analyst in the process of simulating a real system. So because if we make mistake, if we have error on estimating the parameters or fitting a distribution, then the results obtained by that simulation model couldn't be trusted, right? So these are the examples of common pitfalls of data collection: stale data, unexpected data, time varying data, and dependent data. I will have example for any of these common pitfalls in the next slides. Okay, so the data that we have, they may be out of date, or they are maybe dirty, containing errors. So how can we realize that the data are somehow out of date or they are dirty? We need to use our judgment as well, right? We need to have somehow an experience on the context of that system. Then we can use our judgment along with the statistical tools. Then that will actually boost our data modeling process. Okay. Let's have an example for the stale data. Here we're assuming we have a cancer screening clinic, and this center needs a simulation model to investigate different ways of reducing the time patients spend in the clinic. So one part of this process is obtaining the patient's history by a nurse. And in the archive, we have a study that has been done in 2002, and we have the recorded data on the time of doing that task. So can this data set be used for the current project now? So that's the question, right? But after deep investigation, we found that in 2002, nurses stopped recording the screening notes on paper and started to enter the data directly into a laptop computer. So because of that change in the process, the data available from 2002 does not represent the current process anymore. So we can't use them, right? They are out of date, they are stale data. So what's the solution then? So here we may collect new data from the current system if we do have time and we do have the budget to do so. But if not, then we may actually use the estimation provided by the nurses. Okay. Another example for unexpected data. So assume that we have a security screening at a government building, and it includes a metal detector. And we are going to have a simulation model to do some analysis. And in this study, we have obtained 1,000 observation of the time required to pass through the metal detector. Okay. And based on those 1,000 observation, the average time is 0.5 minutes, or let's say 30 seconds, with the same standard deviation. So since the mean is the same as the standard deviation, so here we can say it suggests the exponential distribution is a good fit. I mean, is a good distribution for this data set. But here, the analyst has another opinion. Yeah, based on her experience, it takes just a few seconds to pass through the metal detector, not 30 seconds. So what should we do now here in order to go in more details and more deeper on the data set? So here we can draw a histogram of the collected data. And after having the histogram, we see, oh, we have two categories of the data in the 1,000 data set. So by having the histogram, we see two distinct distributions. So why? Maybe it's because of some people pass without incident and the others trigger the alarm and need to remove remaining metal and try again, right? Or we find out that some people may need personal inspection. If we need to be more accurate, then we need to consider three categories, three distinct distributions. Okay, so and another problem that we observe in this study is negative times. So we have 9 negative data in the 1,000 data. So is it possible? No. It may be small numbers, or we may have mistake on recording, so we can't have negative data, right? So what to do then? We can actually remove those negative data from our data set, so then we will have 9 less than 1,000 data, right? But here now how we can actually estimate the probability of on setting off the alarm. Should we divide 236? Let's say in 236 times people trigger the alarm. So should we divide this 236 by 1000, or should we divide this by 1000 minus 9? So if you're not sure, both should be considered in the simulation to see if there is a substantial impact. Okay. Another example for time varying data. So let's assume that we have a call center of a computer, and this center is working from 8 a.m. to 8 p.m. So we have a solution study in order to obtain the staff levels, and here we obtain uh, the average call per day by having an extensive records of calls. So it's 12,277 calls per day. And it seems that assuming a Poisson distribution is a good fit for this data set. So the average 12,277 calls per day, or let's say 17 calls per minute, could be a Poisson distribution, a Poisson process, right? So yeah, this analysis sounds good, and the choice of Poisson or exponential distributions, because we can say the arrival process is Poisson, and the inter-arrival time will be exponentially distributed, and this is supported by the data. So it looks good, but there are some issues in this analysis. So let's see what are the issues. The arrival rate of call can vary substantially by time of day, or day of week, or time of year. Yeah, so it's not constant, right? So can we assume a stationary process, I mean a stationary Poisson process for the whole year? No, because in a stationary process, we assume that the basic properties do not change over time. But here we see they are changing, right? We will have certainly different arrival rate by time of day, day of week, or time of year, right? So here we need to consider non-stationary process, because in this process we will have rate changes over the time, over I mean the days on week and so on. So yeah, Poisson process would be good, but we need to consider the non-stationary Poisson process, not the stationary one. Okay. And the last example for the dependent data. So here we have monthly demands of a sport drink for a supply chain simulation. So a simple input model here, we assume that the demands over the days are independent and are identically distributed, so IID. So let's see if these assumptions are valid on our dataset. So one informal way here is plotting the demands over the time to see if there is any trend or seasonal pattern. Okay, so yeah, I mean it's somehow a visual investigation, right? So by plotting this diagram, I mean demands over the time, if we observe any pattern, seasonal behavior or trend in the data, then we need to detrend the data first in order to estimate our parameters or fit the distribution. Okay. And for independence, for dependency or independence evaluation, we can plot a time lagged scatter diagram. Okay, so in time lag scatter diagram, we can set a period, let's say a month, then we will actually plot a scatter diagram for demands of month t and month t plus 1. So 1 month lag between the two demands. Okay, so for example, in this time lagged scatter diagram, you see that if we have a low demand in month T, then it will be followed by a high demand in the next month, right? Or if we have a low demand, a high demand in month T, it will be followed by a low demand in month T plus 1. So here for sure there is a dependency between the demands, between the demand of month T and month T plus 1. So that's another way, to observe if there is any dependency between the data. Here for time-related data, and we can try different lags. Month, or let's say a season, a quarter, or year, and so on. Okay. So here we finished on the introduction to chapter 9, and in the next part we're going to we are going to have more details on selecting the distributions and the properties of the distributions and how we can fit a distribution to a data set. Okay, thank you.